It's calculator time.
And his name is John C.
Okay, now let's actually get started using our calculator. So we're going to turn on our calculator here, and we're going to get to the home screen. Now most of you probably already know this about your calculator, but we have a scratch pad and we have our documents. So for this video I'm going to be using the scratch pad mainly because it's easier to use. We can see that we have a calculate and a grapher, which basically is the same thing that we'd use in our documents. So we'll get started with the scratch pad here. So we can go to our scratch pad quick button right here, or we can obviously scroll around with our little mouse thingy right here. But I'll go to the scratch pad thing right here. And so first, before we start anything, College Board doesn't make you do it, but I guess it's good to help clear your variables first on your calculator, and that's always key because you don't want to be plugging in variables that you don't want or numbers that you don't want into equations that you use further down the road. So we're going to start by clearing our variables and clearing our functions. So now you can go to Menu, then you go to One Actions, and you can scroll down and you can see right here we have a clear A through Z. So you can either clear A through Z variables, which are variables that you have stored, which I'll go over later, or you can delete a variable, which is basically a function. But in this case, we want to just delete all our variables right here. So we'll go to 4 and we'll hit 4, and it asks, oh, do you want to clear variables A through Z? We'll hit OK, and you can see right here it's already cleared A through Z, it's done. And so we have all our variables clear and we're ready to start using our calculator. Now it's very important that we clear the variables after each, solving each FRQ or each multiple choice problem, because we don't want to carry over incorrect variables from a previous problem to a new FRQ or multiple choice problem, because that would just mess everything up and that would not be good. So first we'll start off with the solver. So now most of you already know basically what the solver is. If you haven't, then that might be a problem, but anyways, I'll go over it. We can look at more applicable problems like this one. So number 2 right here is actually the 2006 FRQ. Now we can actually use two things here. We can use a define function. We can also use the solver on this. So basically the question's asking for the area between the curves, but to get the area you need to have where you have your intersection points on the two functions listed right here. F of x is equal to ln of x, and g of x is equal to x minus 2. And so you need to find your intersection points, and that just means basically algebraically solving by setting the two equations equal together. So, but we can easily do this and use the define function to our advantage if we go and type in define. So if we type in define using the bottom keypad, you can see that whenever your variables are in italics like that, like right here, that means it's in variable format. However, once you have an actual function and it becomes normal, like it just did with define, that means you're committing to a function. And so we're going to the define function right here. So you just define, space, then you directly just type in f of x is equal to ln parentheses of x. And that parentheses is very important because you just type in ln of x, it's going to think, oh, there's a variable ln of x, when there's actually ln of x is a function. So that was a very important thing, and I actually messed up earlier in the video with it, so I had to reshoot this. But we have that now. And now we can also now define g of x as well. If we just type in the define, I think there is a shortcut to that to do define, but I'm used to typing it in, so I usually just end up typing in define, and it's very fast. But if I do find a way, I'll put in the link below or something else. But you just define g of x as x minus 2, and now we hit the enter button. So you can see right there we have our two functions defined now. We can now just use the solver, and our lives become a lot easier. So we go menu, menu 3, 1, and now we have our solver. If you go f of x is equal to g of x. You have that. You're solving for x to find the x coordinates of intersection, comma x. You hit enter, and you get your two results. Now, disregard that little yellow thing. That's just saying our answers are decimals that are extremely, extremely long, and that these numbers are just estimates of our variables. So that basically gives us our answers right here. And now we have our two x coordinates when the functions intersect. So we basically used the defined function, just made our lives really easy with this little f of x, g of x function, instead of having to set both functions equal to each other, where we could have in the future errors in which we type in our calculators incorrectly. But yeah, that's basically it. You can go through the different formats of how we defined each function. So it's basically define, f of something, g of something, t of something, z of something, a of something, whatever your heart desires. You just have to make sure that whatever your x variable is, right here, what you're plugging in is equal and is used in your function there. So as long as you make sure you can do that, you can solve for functions, you can store it. You can also store variables. Say I wanted to store one of these functions for later use to find the area between the curves, to make things a lot easier. So you can actually go and type in the number right here. So if you were to go 3.14619, and you hit Control and this little variable button right here, if you wanted to store, you just hit that, and it gives you this little arrow. And that basically means, oh, I'm saying that this number is equal to whatever letter variable I give it. So in this case, let's just give it z. So this function is now going to be z. And now we have z is equal to this function. So if we were to actually go through and do z plus 5, we wouldn't get 5. We would actually get whatever this number is, this 3.14, plus 5. So we'd get, in this case, 8.14. So here we can actually store variables and store functions as well. And this is very important, and it's very key to what you're going to be doing with lots of FRQs and all the multiple choice questions. So basically, you can see right here, we have our key things with the solver and the define function that you can copy down and know. And those are the formats and the basic formats you're going to be needing to know. And like as always, you're going to need to always clear your functions and clear all of your variables. So you go menu, action, clear A through Z, and therefore Z is no longer in use, and you're safe to move on to your next problem. And so next we'll be going over the calculus functions and the grapher. Okay, so now we're going to be looking at the calculus functions on the Nspire. We'll get started. We're going to be looking at a 2004 FRQ, the first one on there, because it actually has some good uses that we can put our calculator tools to use. So first I'll start off with integration, because that's mainly part A of the FRQ, and then part B is differentiation. So we'll start off, so here we can see that we have traffic flow, which is the rate at which cars pass through an intersection, and that's shown by this function f of t, where f of t is the cars per minute and t is measured in minutes. And so here, to make our lives a lot easier, especially when we go to integrate it in part A, is that we're going to define the function f of t. So f of t is given, so we're going to go actions 1 to define it, and like we did last time, we're going to go through and define f of t. So f of t is equal to f of t is equal to 82 plus 4 times sine of t divided by 2. So now that we have that, we can hit enter, and there we have our function right there. So now we're ready to start integration. So if you go to menu, and you can go to calculus, obviously, which is 4, it's right there. You can go to integral. So since we're looking for the nearest whole number, and we're trying to see how many cars in total pass through the intersection over a 30-minute period, given f of t as our function of change. So we all know that the function of change if you take the integral, that's our total net, or the total amount at the end of a certain amount of time. And so we're going to find the total amount of cars passing through the intersection over 30 minutes. So we're going to go to integral right here, and just hit 3 to go to integral. And you see this nice little integral thing set up. And so we can actually easily plug in numbers to it. And so just how you'd write any integral, you go 0 to 30, because it's 30 minutes. And now we're going to go to here, and this is where you input your function, right in this center piece right here. And since our function is already defined as f of t, we can just define f of t right here. So we do f of t. And now we just have to fill in dt, which is right here, and that's obviously, it's going to be dt. If you were doing a function in terms of x, it'd be dx in another case, but we just put dt right here, and then hit enter to solve, and we get our answer. Now we do have to convert it to decimal. Now, on the test, they may give the answer like this, in this format, but we have to hit it, convert it to decimal. If they do give us the answer in other formats. So what you're going to do to convert it back into decimals, you hit Control, Enter, and that gives you a more numeric format, and that's the answer right there. And if you go down to the key, you can see the answer as well. So that's how to use the basic integral function. Now, and that's how what type of problem you'd use it for on an FRQ type problem. Now, if we look at part B, we see, is the traffic flow increasing or decreasing at t is equal to 7? And give the reason for your answer. So, this part is actually really nice, because all we're trying to do is find f prime of t. So all we need is f prime of t. And so all we need to do is have this. We just need to find the derivative function. So what you do to go have the derivative function, with time equal to 7, all you need to do is go to Menu, Calculus, which is 4, and you take the derivative at a point. And so here we have, we actually get this pop-up box. Now, if you were to do it the other way, which I'll show later, you can have it, but here we're just going to be looking at this right here. We'll be looking at the value, and our value is going to be 7. We're going to hit OK. And right here, now we're given to find the derivative at a point. And since we want to know what the traffic flow is at t is equal to 7, we're going to use this. But I'll show you the other way to do it in a bit. But and so here we're given this format right here, and all we have to do, it's really nice, we just put in our equation. Actually, I should change this. This should be dt, because we're doing everything in terms of t. This should be t right here. Yeah, t is equal to 7. And now we just put in our f of t function that we defined earlier. And now f of t. And we're going to get our answer. You can simplify that down. And we do get the correct answer, negative 1.87. And so this is a really easy way to do it. But say you just wanted to find the derivative of the function. Now that's even easier. If you just wanted to do that, you just go up there, you hit Menu, 4 to Calculus, and then you just hit 1 for a derivative. You type in what you want as your base changing. So in this case, we're going to have dt. And then we're going to have our function, which is going to be right here. And so, which is f of t. So we have f of t right there. And we can have our derivative at the point. I think we can even do f of 7. If we did f of 7, would that work? No, f of 7 doesn't work. Okay, so you can't do f of 7. So what a thing is, a mistake you don't want to make, which I just made right here, is that you don't want to just plug in the number right there. I mean, we'd never do that in a real problem. So just go and derive the problem first. So here we have the function f of t. We see that the function is defined because it's bold. And now we hit the enter, and we get this. So now that we have this, we can copy and paste Control-Z, or Control-C, Control-V down here. And we can just replace that with our variable, which is, at this point, 7. And so after we do that, we can go to the decimal solving, and we get the same answer. So there really is no huge difference between finding the derivative and the derivative at the point. It's just, oh, do you want to make it easier if you just want to find the derivative for certain problems, or on these FRQ type problems, if you need something specific to a point, then you can use the derivative at a point. And these are all, you can go through all of these calc, different types of functions. They're all basically the same, but what's really nice is that the derivative, their derivative at a point, and the integral, and even the limit as well, and the sums, are all set up nicely, so that all you have to do is just plug in the numbers like you do regularly on a regular format. You don't have to memorize any special equation like the solver. It's very straightforward, and it's very nice and easy to solve. Okay, so now we're going to be going over graphing. And so we'll be looking at the graphing part of the calculator and what aspects and things we can do with it. So first, we'll go to taking derivatives of graphs. So this can be used when you're trying to just, I don't know, analyze a function, see what a function looks like, and identify its slope or how it's moving or how it's tending, or you can find your points of concavity or points of inflection very, very easily by using this function. So you can start off, we're going to start off with a basic x squared function. So we're going to go to menu and graph just a basic x squared or x cubed graph, let's say. So we have a basic x cubed graph right here. Now what's something that's really cool is that we can do is that we can go to the menu and go down to analyze graph, which is right down here on 6. So if we go to 6, we have tons of things that we can do. And now you can see we can find zeros on the graph, which pretty is self-explanatory. You find zeros on which the graph hits the 0 point. You can find the minimum value on a set integral or set boundary. So if I really want to, I can go through and set a minimum or maximum. So I'll do well, I guess it's kind of hard on here, but I'll set a max. Let's go with a max. And so see, now you have this little dragging thing that you can drag around. It's actually pretty cool. So what you can do is that you can set your lower bound right here, and you click it, and then when you start dragging, you actually have your upper bound. And I guess in this case, it's just the end point because this is a x to the third graph. But you can see it actually gives you the x value and the y value. So if you're trying to find the maximum of a function, instead of having to go through the process of doing everything, you can actually just go along here and just drag along to the correct x value that you want and find your maximum y value on a function. And so that makes things really easy when it comes to FRQs or even multiple choice questions. If you're trying to find the maximum of a function that's really complex and you don't have the time to derive it, or you just don't feel like driving it, you can easily do it with this maximum function. So once you do that, it gives you your function maximum as a nice little point, and it looks pretty nice. And that's basically how it works with the minimum. And so you can also do intersection, which I'll go over later, but first we'll look at the dy dx, and that's the derivative of the graph. And so here we can actually see the graph and find the point, and find the dy dx, the slope at the point. So as you can see here, I'm dragging it along, and you can see as we're going down, you can actually see what values we're getting here, and how the slope is slowly going up exponentially as we go. So if you wanted something right here, you could actually find the slope and have the slope at that point. So that's the dy dx at the point. So you can do this for any type of graph. So if they asked, oh, find the slope of blank of f of x at this point, all you have to do is graph the graph and find it and go to it, and then you have your slope right here, and it looks really nice, and they give all these nice little texts. So that's just something that's pretty cool that you can go through mainly through analyze graph. You can do tons of things here. You can find integral, which I'll go over a bit later, maximum mins and zeros and stuff. So I'll demo a 0 here if you want. Set your lower bound up here, and then you go to your upper bound, and it gives you your 0 right here at 0, 0. So now this looks really messy, so I'm going to clean this off a bit and move on to an FRQ that we have. So here we have the first part of the 2004 FRQ. And so I'll get to that. And it's finding the region enclosed by the graphs shown right here. So we have our functions right here, f of x and g of x, and we're trying to find this bounded area right here. So normally you can algebraically go through and solve everything, but because we have such a really nice calculator, we don't have to do that. We can easily just find it and use bounded areas to graph our areas and find the bounded area between it. So first let's start by graphing. So we have our first graph, and that's right here, 2x, or okay, we have to distribute first, so 2x minus 2x squared. We have that, that's our graph right there. I'll zoom in a tad. Zoom, you go menu 4, and then you can go down to 3 for in, and go to the other one for out. And so now we're gonna go put in our second function, which is, I guess if we distribute it all out, it's gonna be 3x to the 3 divided by 2 minus 3x to the 1/2, and we have that. And so yeah, that's our graph. We can see that on the actual function. Now what we can do here is we can find the area between the curves, which is what they're asking for. Instead of having to actually set it up, I mean, this is an FRQ, but if we were to double check our work or do this on a multiple choice question where they don't actually see our work, we can go to here, menu 6, analyze our graph, and we go to bounded area, which is 8. So you can set the bounded area. Obviously, we can see that it starts at 1. So we can put our lower bound. If I can get this to work. Yeah, so we have our bounded area here. And you can move this. It's actually pretty cool. You can move your bounded areas as well. So if you don't like it, you can move it, like I don't like it right there, and move it to the point of intersection. And so it doesn't give a perfect value, but it gives you a rough estimate. And so the rough estimate's 1.13, and I'm pretty sure that's very, very close to what the actual is. Yeah, it's very, very close. If you look closely right there, it's 1.13 on here and 1.133 on the sheet. So if you see here, if you really zoom in, and you can find the area between the curves using menu 6 to analyze your graph, and bounded area at 8. So that's very, very helpful when you're trying to solve for functions and find the area and just double check to see, oh, did I do this right? Did I forget this pi here? And you can easily tell, oh, if you forgot the pi there, then that's fine. You can also find integrals, so areas under the curve. So I'm going to clear this off, delete everything, and just look at a basic x squared graph. We'll enter that in. Now you can find the integral, so area under the curve. So say I wanted to find that, so you go analyze graph 6, and you go integral 7. Now I can go to area under the curve for basically anything, and that's what's really, really nice too, is that it's got such a nice user interface. You can just drag that along, find your points, find your intersection points, and there you have your area under the curve. So that's very, very nice, and it's very precise too. So it's not using any estimations or triangles. It's straight up what the area is. So if you want to double check, oh, is my area right? Did I take the wrong side of the sum? Am I taking the right side? You can easily check it with that, and you get a pretty accurate thing. So for graphing, this is very, very nice. And next, I'll be looking at more slope field equations, and a really easy way to determine slope fields. So we're already given slope fields in this equation. And now this isn't, I guess, well, this method would be really good for slope fields in graphing differential equations. So here we have a slope field FRQ. And so usually for part A of these slope field FRQs, even though they're really a gift, you can always double check how your slope field is going to look like if you were to actually graph the slope field. So first we'll clear everything. Okay, that's clean. Now we go to graph entry, and instead of going to 1 for function, this time we're going to go all the way down to 7 for differential equations. And now we're given our equation right here. It's dy over dx, or y prime, is equal to x squared times y minus 1. Now, if you look on the calculator, we technically have that format already set up. We have a y1, and that's very nice because that's technically the y prime, or dy over dx. So now all we have to do is go this. We just go y squared, and then we go y1. Actually, I have to go back. Y squared times y1 minus 1. Right? And so now that we have that, it becomes really easy, and we just hit the enter button. We always have to make sure that y1 is replacing the y in some part of the equation. So it's very key that we have this y1 minus 1 instead of a y minus 1, because if you don't have that, so if I tried to do it like that and I didn't have it, it wouldn't graph anything. So it's important that you have that y1. So we have our y1 right there. And now we have our differential equation. And you can just basically use this to graph what you need in part A. So as you can see, part A looks a lot like what's on the calculator for the regions wanted or regions desired, and see how the graph is tending and stuff like that. So it's a very nice, cool, easy thing to use. So basically overall in the video, there's a couple more things that I could have gone over as well. There's tangent line approximations you can do. There's function maximum minimums as well. So those are all pretty basic, but these are basically the formats you'll be looking at for those. But overall, everything else is pretty basic. I mean, if you go through, we have the solve and define functions, and these are really, for any math class, going to make your life a lot easier and a lot better for all aspects of solving equations. And even on the SAT, you can use the solver or define functions to make your lives a lot faster and check everything more quickly and more efficiently. And I feel like if you really master the solver and the define function, you'll be basically set for any other function, because all you have to do is plug in, show your work for all these other types of rate of change problems, and then once you have your work all set up, then you can basically just plug everything in on your calculator, and you just give the answer, because the answer is just 1 point. You should really be focusing on your work. If you're having to spend a lot of time doing all the algebra, it's not really worth it. And that's basically it. Thank you.